Hello everyone. I hope you are very well. Today I am going to give you a presentation on pulse amplitude modulation. That is, in short, it will be PAM. It is popularly known as PAM. So it is a very important topic in case of digital communication system. What will be the outline of the presentation topic of today? It will be pulse analog modulation, types of pulse modulation, and pulse amplitude modulation. This is the last thing you have to learn this. Let's start. Pulse analog modulation. In analog modulation system, some parameters of a sinusoidal carrier is varied according to the instantaneous value of the modulating signal. That means in case of analog modulation system, some parameter of a carrier is varied according to the instantaneous value of the modulating signal. In pulse modulation methods, the carrier is no longer a continuous signal, rather it will be a series of pulses. That means a pulse train, some parameter of which is varied according to the instantaneous value of the modulating signal. Now, these are the types of pulse modulation. So, pulse modulation can be of two categories: pulse analog modulation and pulse digital modulation. And pulse analog modulation can be again classified into three categories. That one's PAM, pulse amplitude modulation, PWM, pulse width modulation, and third one is the PPM, pulse position modulation. And in case of pulse digital modulation, it will again be categorized into three. First one is the PCM, pulse code modulation. Next is the DPCM, differential pulse code modulation. And the last one is the DM and ADM. DM means delta modulation and adaptive delta modulation. So now start with the pulse amplitude modulation. The amplitude of the pulses of the carrier pulse train is varied in accordance with the modulating signal. I told you earlier. And that is, amplitude of the pulses depends on the value of MT during the, MT means message signal or modulating signal, during the time of pulses. So you see this from the diagram, that is, this is a sine continuous modulating signal, and this will be some pulse train, that is the square wave pulse train. Some portion is on and some portion is off, and this will be the PAM signal. That means according to the instantaneous value of the modulating signal, these pulses are varied with this amplitude, with this accordance with the amplitude. So it makes like pulses, but in this way. So PAM is like this. Now, pulse amplitude modulation, what is that? In fact, the pulses in a PAM signal may of flat top type or natural type or ideal type. That means PAM is of two types. One is the flat top type, another one is the natural type or ideal type. The flat top PAM is most popular and widely used because of that. Flat top PAM is that during the transmission, the noise interferes with the top of the transmitted pulses. So all the noises are accumulated in the top of the pulses, and this noise can easily be removed if the PAM pulses are as flat top. In the second case, in natural samples PAM signal, the pulses have varying top in accordance with the signal variation. Such type of pulse is received at the receiver. It is always contaminated by noise. That means it is always merged with some noise, and then it becomes quite difficult to separate this noise or to determine the shape of the top of the pulse, and thus amplitude detection of the pulse is very difficult and very complex system, and rather obviously it will not be the exact one. Next, generation of PAM. There are two operations involved in the generation of PAM signal. First one is the instantaneous sampling of the message signal MT every TS seconds, where the sampling rate of Fs is equal to 1 by Ts, and it is chosen in accordance with the sampling theorem. And second is the lengthening the duration of each samples so obtained to some constant value of t. So that means here it is using a continuous waveform, you have to take some pulses with every Ts seconds apart, and these signals are with the accordance value with the amplitude of the continuous waveform. Here it is the circuit. It will be a sample and hold circuit for generating a flat top sample PAM. So here it is using a G1 and G2. G1 is the one type of FET and G2 is another type of FET. And this FET, one FET is used as sampling switch and another FET is used as discharging switch. And in this circuit there will be a capacitor which will actually holds the charges. So here how it operates. A sample and hold circuit shown in the figure is used to produce a flat top sampled PAM. The sample and hold circuit consists of two FET, that is the field effect transistor, switches and a capacitor. The sampling switch is closed for a short duration by a short pulse applied at G1. That is, G1 is the gate of FET 1 and G2 is the gate of FET 2. So the sampling switch is closed, this one. The sampling switch is closed for a short duration by a short time or short pulses applied to the gate G1. During this period, the capacitor C is quickly charged up to a voltage equal to the instantaneous sample value of the incoming signal xt, this one. Now the sampling switch is opened and the capacitor C holds the charge. The discharge switch is then closed, this one, by a pulse applied to gate G2 of the other transistor. Due to this, the capacitor C is now discharged to 0 volts. This discharges switch is then opened and thus capacitor has no voltage. Hence, the output of the sample and hold circuit consists of a sequence of flat top samples as shown in the figure, second figure, this one. So you see here it will be when G1 is on, we get a pulse like this, and when it is off, the discharge is coming like this, and discharging is coming like this, and it will be off again. That is, the capacitor will be discharged fully. This capacitor discharges fully. Then again you have to switch on the sampling switch. Then again it will be rising in the capacitor charges. Then it holds some charges, and when sampling switch is cut off and G2 is now on, that is discharging switch is on, now it will becomes charging in its discharging state. So in this way we get a flat top sampled value. Here this operation is writing what I said earlier. So now mathematical representation of PAM. We may express the PAM signal as St is equal to summation n is the number of samples, it becomes minus infinity to plus infinity. It becomes m of nts into ht minus nts, where ts is the sampling period, m nts is the sample value of mt, where t is nts, and ht is the standard rectangular pulse of unit amplitude, and duration t, and it is defined as ht is equal to 1 when small t lies between 0 and capital T. It will be half when t equal to exactly 0 or t small t is equal to capital T, or 0 values otherwise. The spectrum of flat top PAM signal is now SF is equal to Fs, that is the sampling frequency, summation k is equal to minus infinity to plus infinity, m of f minus kfs hf. That means the earlier time domain signal, this one, is now converted into frequency domain. So it becomes like this. Next is naturally sampled PAM signal. The natural sampling is basically pulse amplitude modulation. Therefore, it is called naturally sampled PAM signal. The time domain representation of a naturally sampled PAM signal will be given as St is equal to tau A by Ts, summation n is equal to minus infinity to plus infinity, mt sine of c, that is sinc function actually, fn tau e to the power j 2 pi fs tau. That means it will be a exponential function. And the frequency spectrum of naturally sampled PAM signal will be like this. That is SF is equal to, this is the time domain function, and this will be the frequency domain representation. SF is equal to tau A by Ts, summation n is equal to minus infinity to plus infinity, sinc function of nfs tau, x of f minus nfs. That is e to the power j 2 pi fs tau is now becomes x of f minus nfs. Next is ideally sampled PAM signal. The instantaneous sampling is basically PAM. It's called ideally or instantaneously sampled PAM signal. The time domain representation of an ideally sampled PAM signal will be given as St is equal to summation n is equal to minus infinity to plus infinity mnts delta function. It will introduce a delta function of t minus nts, and the frequency domain representation, that means frequency spectrum of an ideally sampled PAM signal, will be given as SF is equal to Fs sampling frequency summation n is equal to minus infinity to plus infinity x of f minus nfs. So this whole thing will be converted into x of f minus nfs. Now, transmission bandwidth of PAM. In PAM signal, the pulse duration tau is assumed to be very small compared to the time period Ts. So that means tau is very, very less than Ts. If the maximum frequency in the modulating signal xt is Fm, then sampling frequency Fs is given by Fs must be greater than or equal to twice Fm. This is according to the sampling theorem. Or 1 by Ts must be greater than or equal to 2 Fm. Or Ts must be less than or equal to 1 by 2 Fm, that is half of Fm. Therefore, tau is very, very less than Ts. So that means it is very, very less than 1 by 2 Fm. If on and off time of PAM signal is equal, then maximum frequency of PAM pulse will be f max is equal to 1 by tau plus tau. That means 1 by 2 tau. Therefore, transmission bandwidth must be greater than is equal to f max. But f max is equal to half of tau. We get here from this equation, earlier equation. So bandwidth equal to must be greater than is equal to 1 by 2 tau. That means bandwidth must be greater than is equal to 1 by 2 tau or very, very greater than Fm. So this is becomes bandwidth must be very, very greater than Fm. This is the bandwidth requirement, transmission bandwidth requirement of PAM signal. Next is demodulation of PAM. Here it is seen that PAM signal is constructed and now PAM signal is transmitted and it will be received by a reconstruction filter, and from this reconstruction filter there will be an equalizer and we get back the original message signal, that is the modulating signal. The distortion caused by the use of PAM to transmit an analog information bearing signal is referred to as the aperture effect. This distortion may be corrected by connecting an equalizer in cascading with the low-pass reconstruction filter as shown in the figure. That means there will be some distortion that will be caused by the PAM signal and it will transmit an analog information bearing signal is referred to as the aperture effect. And this distortion may be corrected by connecting an equalizer in cascade with the low-pass reconstruction filter as shown in the figure. And the equalizer has the effect of decreasing, and it will actually decreasing the in-band loss of the reconstruction filter. That means if there will be some inbuilt losses during the reconstruction filter forming the equation or forming the signal, then equalizer effect is decreasing. As the frequency increases in such a manner, there will be compensation for that aperture effect. So that means whatever will be the aperture effect in your reconstruction filter for reconstructing the message or modulating or information signal rather, that aperture effect must be compensated with the value of equalizer effect by decreasing the in-band loss with the increasing frequency of the reconstruction filter. So this will be happened in case of demodulation of PAM. So now ideally the magnitude response of the equalizer is given by, this is the 1 by HF, that is the response factor will be 1 by T sync of Ft, that is pi f by sine pi Ft. That means this amount of equalization needed in practice to specify and usually make it small for demodulation of PAM. So if this equalization amount in practice will be usually make small, then demodulated output, that means your modulating or information signal will be well reconstructed from your original modulating signal which is coming from your source. Okay. So now what will be the advantages of PAM? It is a simple process for modulation and demodulation. That means in case of modulation and demodulation, there will be no as such circuitry or device will be required. It is a very simple circuitry in case of modulation and as well as demodulation. Transmitter and receiver circuits are very simple and easy to construct. You see that in case of modulation, we need some two FETs and a capacitor, and in demodulation, we need a reconstruction filter only and an equalizer. That's all. And what are the drawbacks of PAM signal? The bandwidth required for the transmission of a PAM signal is very large. This is very, very crucial thing, as it makes a drawbacks of PAM signal. That is, the bandwidth requirement is very high in comparison to the maximum frequency present in the modulating signal. Second one is since the amplitude of the PAM pulses varies in accordance with the modulating signal, therefore the interference of noise is maximum in a PAM signal. This noise cannot be removed easily. We see that in case of flat top, we minimize the noise at the top position of the samples, and in case of naturally PAM signal or ideal PAM signal, there will be very difficult to eliminate that noises. So it will be a very big drawback of PAM signal. And since the amplitude of the PAM pulses varies, therefore this also varies the peak power requirement by the transmitter with modulating signal. That means amplitude of the PAM pulses varies. So therefore the power requirement, peak power requirement is also varies in form of transmitter to modulating the signal. So these are the three drawbacks of PAM signal. First one is the bandwidth requirement is very high. Second one is the noise will not be eliminated or removed easily. And the third case, the peak power requirement is varying. It will not be make a constant value. It has to be a varying value using a transmitter of modulating signal to transmit the modulating signal. So these are the drawbacks of PAM signal. These are the very important drawbacks. Now, what we learned from this presentation, I hope you enjoyed this presentation very well. We learned from this presentation will be pulse analog modulation, what are the types of pulse modulation, and it is very important that we learn whole about the PAM, that is the pulse amplitude modulation. That is generation, how to generate it, natural and flat top PAM, the mathematical analysis of PAM, transmission bandwidth, what will be the transmission bandwidth in case of PAM, the demodulation, advantages and drawbacks. So whole about the pulse amplitude modulation. So I hope you enjoyed this presentation very well and you learn about the pulse amplitude modulation very well. So that's all for today and thank you very much.